Hello friends, in this video let's work out some problems on heat that involves specific heat, latent heat, and also the transfer of heat through conduction and radiation. So those are the main topics. So here is the first question. On a hot day, the temperature of an 80,000 liter swimming pool increases by 1.50 degrees Celsius. What is the net heat transfer during this heating? Ignore any complications such as loss of water heat or water by evaporation. So you have an 80,000 liter swimming pool. Temperature increase is 1.50 degrees Celsius. Now, liters is a unit of volume. First of all, we need to change that into kilograms, which is the unit of mass. So 80,000 liters is actually 80,000 kilograms of water. Because 1 liter of water, and this applies only to water, 1 liter of water is 1 kilogram of water. So first you get the mass of water, and then you have the change in temperature, and then you need to know the specific heat of water that will be given. 4,186 joule per kilogram per Celsius. So once you have these three quantities, it's just a matter of using the formula to multiply these three quantities and find the heat transfer. So let's do that. So density is mass by volume. I'm trying to show you how to get the liters into kilograms. So mass is density times volume. And the density of water is 1,000 kilogram per meter cube. Or that's supposed to be 10 to the power 3, not 10 to the 13. So let me correct that. That's a terrible mistake there, right there. So this is supposed to be 10 to the 3 times 80,000, okay, times 1 meter cube by 1,000, because 1 meter cube is 1,000 liters. Okay, this is the longer method to change the liters into kilograms. So that gives you 80,000 kilograms, as you can see. Just remember, 1 liter of water is 1 kilogram. That's easy. And once you get that, Q is mc delta T. M is the mass, C is the specific heat, delta T is the change in temperature. So you have the mass, the specific heat is a constant for water, which is given, 4,186, multiplied by the change in temperature. Remember, the change in temperature could either be in Celsius or Kelvin, because if it's change in temperature, it's the same thing. If it is change, it's the same thing. So you get the answer as 5.02 times 10 to the power 8 joules. Obviously, that's a lot of heat because there's a lot of water in it. So that's number one. Moving on to the second one, the same heat is transferred into identical masses of different substances and produces different temperature changes. Calculate the final temperature when 1 kilocalorie of heat transfers into 1 kilogram of the following, originally at 20 degrees Celsius. So what you have is 1 kilocalorie of heat. See, kilocalorie is a practical unit of heat. And if the quantity of heat is given in kilocalories, then the specific heat used must also be in kilocalories. So first we're dealing with water. We have the mass of water. Mass of all of these substances is 1 kilogram, as you can see there. 1 kilogram is the mass. Specific heat will be given for water, and the quantity of heat that comes in is 1 kilocalorie. So that's Q. Q is 1 kilocalorie. Heat that's coming in, mass is given. So I'm going to show all the work together. It's a printout, so it's going to come up. Q is equal to mc delta T. That's the formula we're going to use. We have to find the change in temperature, so let's make that the subject. And you get Q by mc. Q is what? 1 kilocalorie. So 1 kilocalorie divided by the mass of water is 1 kilogram. And then we need the specific heat of water, which is 1 kilocalorie per kilogram. So that's the specific heat of water. Easy to remember, 1 kilocalorie per kilogram. When you do the calculation, all of this is 1, so you get 1 degree Celsius. That's the change in temperature. So the final temperature would be 20 plus the change, which is 1, so 21. So in the same way, we have to work out all the others. The only quantities that change, in fact, the only quantity that changes is the specific heat. As you can see for this, it's 0.20. What is that? That's concrete. Then for steel and for mercury. Because the specific heats are different, the change in temperature is going to be different. Notice that if the specific heat is smaller, then the change in temperature is higher. Take a look. So you look at mercury, that has the smallest specific heat here. It's only 0.0333. And that's why you have the biggest change in temperature. What do we get? We got 30 as the change in temperature. See? Remember that. So lower the specific heat, higher the change in temperature. So that's number 2. Number 3, the number of kilocalories in food is determined by calorimetry techniques in which the food is burned and the amount of heat transfer is measured. So on food packets, you find how many kilocalories you would get by consuming that food. We've all seen that. So here the question is, how many kilocalories per gram are there in a 5-gram peanut? So you only have 5 grams of peanut, and we have to find how many kilocalories are there per gram. If the energy from burning it is transferred to 0.5 kilogram of water held in a 0.1 kilogram aluminum cup, causing a 54.9 degrees Celsius temperature increase. What's going on? So the energy that you get by burning 5 grams of peanut is transferred into 0.5 kilogram of water, which is in an aluminum container. And there the change in temperature is 54.9 degrees Celsius. So from these results, we have to calculate how much energy was there in 5 grams of peanut, and then finally divide that by 5 to get the energy in 1 gram of peanut. All right, so I'll explain it after I put all the results down. Like that, I'm going to explain. So first of all, the quantity of heat is gained by water and aluminum. So mass of water times specific heat of water times change in temperature plus this is the heat gained by aluminum. Mass of aluminum times specific heat of aluminum times the change in temperature. Now they both went through the same change in temperature, so that's taken out. You see the delta T is taken out, and then you just have these quantities inside the parenthesis. So now substitute. This is the mass of water. This is the specific heat of water plus the mass of aluminum plus the specific heat of aluminum. Remember, all these quantities, constants, will be given times 54.9 degrees Celsius, which was the change in temperature. When you do that, you get 28.63 kilocalories. So that's the quantity in 5 grams. So to find how much was there in 1 gram, you got to divide by 5, and that gives you 5.73 kilocalorie per gram. So you get, when you eat 1 gram of peanuts, that's the amount of energy that you get. And then there is a B part that says, compare your answer to labeling information found on a package of peanuts and comment on whether the values are consistent. Okay, a label for unsalted, dry, roasted peanuts says that 33 grams contains 200. Did you notice? Actually, they say calories. You know, that's a kind of trick. It's not calories, it's actually kilocalories. So whenever food packets show calories, it's actually kilocalories. Okay, notice that? I guess they don't want to scare us. So there's 200 kilocalories in 33 grams. So in 1 gram would be 200 by 33, which is 6, which is consistent with our results in part 8. Right? So that's question number 3. And now question 4. How much heat transfer is required to raise the temperature of a 0.750 kilogram aluminum pot containing 2.50 kilogram of water from 30 degrees Celsius to the boiling point and then boil away 0.750 kilogram of water? All right. First of all, notice that there are 2 substances. Water is contained in the aluminum pot. Another thing is that there are 2 processes involved. First, from 30 degrees Celsius, the water has to be brought to boil, which is 100 degrees Celsius. So, first of all, heat is required to change the water from 30 to 100. That's the first process. And the second process is once water gets to boil at 100 degrees Celsius, it becomes steam. So remember, this is a phase change. And when there is a phase change, the formula used is to find the quantity of heat is just mass multiplied by latent heat. Okay? So there's a new formula coming in here. So there are 2 processes. The first process is just a heating process. So the formula is MC delta T, MCAT. And the second process is a phase change. So the formula used is mass times latent heat. When you add up these 2, you would get the total amount of heat required. That's what we're going to do. And there's a B part which we'll come to later. So here in the first part, the quantity of heat required. All right, so you see 3 parts. Why? Because first of all, water has to get heated, then aluminum has to get heated, and then, remember, for the phase change, it's only water that's having the phase change. Aluminum is staying as aluminum. It's not melting or anything. So that's why there are 3 parts. So this is the mass of water, specific heat of water, times the change in temperature is 70. Why? 100 minus 30. Went from 30 to 100, so the change is 70. And then for aluminum, mass of aluminum, specific heat of aluminum, and the same change in temperature. Okay, that's the second one, plus the mass of water that was boiled off was 0.750 kilogram. The problem states that. Times the latent heat of water. The latent heat of vaporization of water. Again, that's a constant that's given. 539 kilocalories per kilogram. When you do all those calculations, you get 591 kilocalories. Okay? And then the B part says, how long does this take if the rate of heat transfer is 500 watts, which is 500 joules per second? So how much time do you need, assuming that you're using an electrical heater to boil the water and to boil off a part of it? How much time does it take? So here the only thing required is the definition of power. Power is work over time, or power is, in this case, heat over time. So Q becomes P times T, because P is Q by T. You heard me. Power is Q divided by time. So Q is power multiplied by time, from which you get time is Q by P. And then we know that the Q required was what? That much. But here, once again, there is a problem because you can't have Q in kilocalories and P in watts. So what we did is we multiplied it by 4186 joule to change the kilocalories into joules. So let me write that right now. So remember that 1 kilocalorie is 4,186 joules. So that's why we multiplied with 4,186 in order to change the kilocalories into joules. So I hope you understand that. So we have number 5 here. A 0.250 kilogram aluminum ball holding zero point 0.8 kilogram of soup at 25 degrees Celsius is placed in a freezer. Okay, there's a certain amount of soup in an aluminum bowl kept in a freezer. What is the final temperature if 377 kilojoules of energy is transferred from the bowl and soup, assuming the soup's thermal properties are the same as that of water? So that means you can take the specific heat and latent heat of soup as being equal to that of water, okay? The problem here is the energy transferred is given in kilojoules. So 377 kilojoules need to be converted into kilocalories, for which we will divide by 4.186, because 4.186 joules is 1 kilocalorie. You will see that first. So that's one thing. Second idea is that when you keep it in that freezer, we have to first calculate how much heat is being absorbed. Okay? How much heat is being, you have to find the final temperature, right? So you have to find how much heat is being lost. Let's do that. So the quantity of heat that is lost by aluminum and then by the soup. So again, mass times specific heat times change in temperature. So that's the mass of aluminum, specific heat of aluminum given, and then change in temperature is taken out common. This is the mass of soup. That is the specific heat of soup, which is that of water. And then multiplied by change in temperature, could be in Celsius, remember. So you get 21.34 kilocalories. That much is already gone when the soup cools from 25 to 0. So listen carefully here. Before you freeze it, you got to change its temperature from 25 to 0, right? So this is the amount of heat required to cool the soup and the aluminum from 25 to 0. Okay. So that is the heat required. So that leaves us with 90 kilocalories was given. Remember 377 divided by this was 90 kilocalories. Out of the 90 kilocalories, we have 21.34 kilocalories gone, leaving us with 68.66 kilocalories to freeze all the soup. Okay, so that means now you got 68.66 kilocalories minus 63.84 kilocalories, which is 4.82 kilocalories to be removed. So we also need to find out how much heat is required to freeze the soup. And for freezing, the formula is mass times latent heat. So here you can see that the mass of the soup is 0.8. Let me use this 0.8 times the latent heat is 79.8. So to freeze the soup, you need 63.84 kilocalories. So we have 68.66 remaining, out of which 63.84 is gone in order to freeze the soup, which gives us 4.82 kilocalories. Okay, so using this 4.82 kilocalories, both the container and the soup will be further cooled from 0 down. Okay, so there are three processes here. Number one, the temperature had to go from 25 to 0 for both of them. Number two, the soup had to be frozen. And number three, whatever heat is remaining, that is being used to lower the temperature of the container and the soup to a particular temperature, which we're going to find. That's where we use this formula. T final is negative because it's being taken out, divided by mass times specific heat of both of these. So you can see the formula is quantity of heat is, we've done this so many times, mass times specific heat of aluminum plus mass times specific heat of soup times the change in temperature. Remember that the temperature goes from 0 to a lower temperature. So higher temperature is 0 minus TF. That's where you get the negative, if you notice. So the TF becomes negative that by that. So we have negative 4.82 kilocalories divided by that, and that gives us negative 10.6 degree Celsius. Difficult? Yes. Why? Because there are three processes. Understandable? Oh, yes, of course, with a lot of concentration. So I hope you got that. Thank you. All right. Here is problem number 6. A 0.05 kilogram ice cube at negative 30 degrees Celsius is placed in 0.4 kilogram of 35 degrees Celsius water in a very well insulated container. What's the final temperature? Okay, so you have an ice cube which is very cold, just a small piece, at minus 30 degrees Celsius. And this piece of ice is kept in or immersed in 0.4 kilogram of water in a container. So the mass of the container, nothing about it is mentioned, so we can forget about it, which means it doesn't appreciably absorb heat because it's an insulator, see? So when you put that ice cube into the warm water, first of all, the temperature of ice is going to go from negative 30, it'll increase to 0 degrees Celsius. Okay? Ice will not melt at negative 30 degrees Celsius. In order for it to melt, the temperature has to go from negative 30 to 0 degrees Celsius. So that's the first process. And that process is just heating of ice. Ice is not melting. And when you heat ice or heat anything, the formula uses this mass times specific heat times change in temperature. So we need the specific heat of ice, which will be provided. But the second process is once ice gets to 0 degrees Celsius, it's going to melt. That is a phase change. So the formula will be mass of ice times latent heat of ice. Okay? So when you add those two, you get how much heat is required. Once we find that, we will be able to find the final temperature. Now follow along carefully, because I'm going to show all of it, but explain it. Don't be worried. First, bring the ice up to 0 degrees Celsius and melt it. So you see that? Both the processes, as I explained. So you have MC delta T1 plus MLF. The sub F stands for fusion, which means melting. So that's the mass of ice. This is the specific heat of ice, which is 0.5 kilocalorie per kilogram. So remember, it's half of that of water anyway. Change in temperature is 30. Why? Because it's 0 minus minus 30. 0 minus minus 30 is 30. Plus that's the latent heat of fusion of ice, which is 79.8 kilocalorie per kilogram. So what is done here is the mass is taken out common. You see that? The mass is taken out common because you have mass here and you have mass here. When the mass is taken out, all you got to do is the specific heat multiplied by the temperature plus the latent heat. Okay? When you do that, you get 4.74 kilocalories of heat. This is going to lower the temperature of water by something. We don't know that. Okay, that's what we're trying to find. Remember, the water in the insulated container is losing heat because the ice is getting heat from there. So the water is going to cool down. Let's find out how much it cools down. So it's normal cooling. So it's Q is equal to MC delta 2, where Q1 we just got now. This is the heat lost by the water. See that? Divided by the mass of water in the container is 0.4 kilogram. That's the specific heat of water. And you get 11.85 degrees Celsius. So the water was at 35 to begin with. It's now lost that much temperature. That's a change in temperature. So the temperature now is 23.15 degrees Celsius. Now this is a tough problem on many accounts. So the water has now reached what? 23.15 23.15 degrees Celsius. But we know when you mix a hot substance with a cooler substance, the heat lost by the hot one is equal to the heat gained by the cold one. Heat lost is equal to heat gained. So what we're going to do is we're going to see the mass here times the specific heat times the change in temperature. Here it stands for C, means cold. Okay? Final temperature minus the temperature is equal to, this is the mass of the hot one times the specific heat of water times that. Okay, so now you have water. This is confusing because once ice melts, what do you have? You have water. So you have the water that comes from the melting of ice on one hand, and second, you have the water that's already warm in the container. All right, so that warm water in the container is losing heat, while the ice that turned into water, which is at 0 degrees Celsius after it melts, is now going to gain heat and go to some temperature. So what's this? So the ice, which melted and became water, is at 0 degrees Celsius, all right? The warm water in the container is at how much? Is at 35. So this water at 0 is going to absorb heat, so its temperature is going to go up, while this water that's in the container is going to lose heat, so its temperature is going to come down, and there's going to be a meeting point. So finally there will be a final temperature, which is what we're trying to find. So look at it carefully. You should understand it's not just the math, it's here you have 0.4 kilogram, which is the warm water there, times 296.3 Kelvin. It's all temperatures are in Kelvin now, changed into Kelvin. Okay, you get that by adding 23 to 273. Okay, so that's how you get that. Plus, this is the water that came from ice melting, so that's the mass. And remember, it's at 0 degrees Celsius, or 273.15 Kelvin to be precise. So that's why you have 0.15 changed to 0.3, because you're taking 273.15 and adding. Okay, divided by the total mass. This is the total mass. And that gives you 293.7 Kelvin. If you subtract 273 from 273.15, you get 20.6 degrees Celsius. That is a tremendous question. So the summary is the ice first has to get heated up to 0 degrees Celsius, then has to melt, but the melted water is at 0. And then the water in the container, which is at 35, loses heat. This one gains heat, and then they finally have a temperature of 20.6 degrees Celsius. So I think if you can do this problem, I think you can do almost any problem in this context, because this involves everything. It involves heating, it involves change of phase, and then on top of that, you also have to use heat lost is equal to heat gained. So that's why I've taken a longer time to explain this. I hope you understand that. So that's number 5. That was number 6. And then it's a different topic now. This is conduction. Conduction is when heat transfers through, for example, the walls of a room in summer. So the outside is hot, the inside is cooler because of the AC running. So heat is continuously coming in. So if this is the wall, you have a temperature on the outside, you have a temperature on the inside of the wall. So you have two temperatures. You have the thickness of the wall, all right? And heat coming in depends on the time taken. So you will have more time, then there will be more heat coming in. So you will have Q, which is the quantity of heat conducted, and you will also have little t, which is the time. And then you have a constant, which is thermal conductivity. So we want the thermal conductivity to be small. That's why, in the walls you have insulation, which doesn't allow so much heat to come in. So you have all those quantities. in the formula, and you can see. Let's go there after we read the problem. Calculate the rate of heat conduction. Okay, what do you mean by rate? Means per second. So how much heat is conducted per second through house walls that are 13 centimeter thick? Oh, so that's the thickness, 13 centimeter. And that have an average thermal conductivity, excuse me, that's the constant thermal conductivity, twice that of glass wall, which will be given. Don't worry, it'll be given. Assume there are no windows or doors. Just to make things easy. The surface area of the walls, the area of the walls is also important. I forgot to mention that. Because if the wall is bigger, then there is more area for the heat to come in. So the area, and the inside surface is at 18 Celsius, outside is at 5. So, this is a cold day. This is not summer. Why? Because the outside is at 5 degrees Celsius, the inside is at 18. So you have the room heater going on. And then we have a second part. We'll get to that later. So we have to find the quantity of heat conducted in a second. Here it is. This is the formula for conduction. Q by T is K, which is the constant, thermal conductivity, A times T2 minus T1. T2 is the higher temperature, T1 is the lower temperature, and D is the thickness. So here is the value given here 2 times. Why? Because this is the conductivity of glass wool. The problem said it's twice that of that, so that's why 2 times. So that's K. Whole thing is K. Then you have the area, 120 meters squared, proper units, meter squared. And then you have temperature, bigger minus the smaller, divided by the thickness, which was 13 centimeter. Of course, you need it in meters, so it's 13 by 100.13. When you do that calculation, you get roughly 1010, right? 1010? Yeah. 1.01 times 10 to the 3 joules per second. Joules per second is watts. And then the B part says how many 1 kilowatt room heaters would be needed to keep up, because heat is continuously being lost. How much would you need to produce? Same as that is lost. And what is lost is approximately 1 kilowatt. So you need just one 1 kilowatt room heater. I hope that makes sense. All right, so here we have question number 8. For the human body, what is the rate of heat transfer by conduction through the body's tissue with the following conditions? The tissue thickness is 3 centimeter. The change in temperature is 2 degrees Celsius. The skin area is 1.50 meter cube. How does this compare with the average heat transfer rate to the body resulting from an energy intake of about 2,400 kilocalories per day? No exercise is included. Okay, let's go again. For the human body, what is the rate of heat transfer by conduction? So that's conduction through the body's tissue with the following conditions. So the tissue thickness, which is D, is given. Change in temperature, which is the difference between the outside and the inside, is 2 degrees Celsius. And the skin area is given. So let's do it. It's conduction, formula is Q by T, is Ka, difference in temperature, by D. All right, so Q by T here is there. That is the thermal conductivity of the tissue, which is given. Then you have the area in meter squared, and then the change in temperature is 2 Celsius. Thickness is 3 centimeter, which is 3 times 10 to the negative 2 meter. You do that, you get 20 joules per second. On a daily basis, this is, because that's per second, so if you convert it by multiplying with how many seconds are there in a day, you are going to get 1,728 kilojoules per day. That's what you need. And the daily food intake is given as 2,400 kilocalories per day. And to change kilocalorie into joule, you multiply with this 4186, and you would get 10,050 kilojoules per day. Okay, so that means you are getting that much, and what is needed is only 17.2% of the energy intake. How do you get that? This divided by this times 100. So 17.2% of energy intake goes as heat transfer by conduction to the environment. So that is lost by the human body to the environment, okay? And the rest is used for everything else, exercise and all that stuff. And to watch this video, especially because you need a lot of energy to watch and concentrate. Believe it or not, when you're thinking, concentrating, you need a lot of energy. So that's 8. Number 9, how many kilograms of water must evaporate from a 60 kilogram woman to lower her body temperature by 0.750 Celsius? This is evaporation, so is this a reasonable amount of water to evaporate in the form of perspiration, sweating, assuming the relative humidity of the surrounding air is low? You know, when the humidity is low, that's when you sweat more. You know that, right? Evaporation is more. So that's why when it's humid, the sweat that comes out stays on the skin and you have that wet feeling that's not so good. But if the humidity is low, then the sweat that comes out evaporates immediately, cooling the body, making you feel good. So to do this problem, mass times specific heat times change in temperature. Okay? So that's the mass of the person. This is a specific heat of the person, specific heat of the human body. Again, all these constants will be given. The change in temperature is given as 0.750 Celsius. And then this is where you have mass times latent heat of vaporization at 37 degrees Celsius. So that's the mass of sweat. So that's what you're trying to find. How many kilograms of water must evaporate? So in the form of sweat. So you're trying to find that. This is the latent heat of vaporization of water, which is given as 580 kilocalories per kilogram. Okay? So here's the mass of the person, specific heat of the human body, change in temperature, and then divided by the latent heat of vaporization of water. That will give you how much evaporated. And then is it reasonable? Yes, 64.4 grams of water is reasonable. If the air is very dry, it says, sweat may evaporate without even being noticed. Yeah. If there's less humidity, it'll just go off fast. You won't even notice. All right, so that is number 9. Number 10 deals with radiation. So radiation involves another formula. Radiation depends on so many quantities. If you have a hot object, how much it radiates depends on the surface area. Okay? It depends on the surface area. It depends on the color of the surface. Black objects radiate more, and that's given by a quantity called emissivity, the little e that's going to come. For black objects, the emissivity is 1. Okay? And then depends on the area, like I said, the surface area, the emissivity, it depends on the temperature in Kelvin of the object that is radiating. It also depends on the temperature in Kelvin of the surroundings. Too many quantities, right? But when you see the formula, you'll understand more. So let's get into that problem. So the problem says at what net rate does heat radiate from a 275 meter square? So that's the area. Black roof, see? Black roof on a night when the roof's temperature is 30 Celsius, got to be in Kelvin, and the surrounding temperature is 15 degrees Celsius. You have both the temperatures, and the emissivity of the roof is 0.9. So although it's black, it's not 1, it's very close. We also have a constant involved, which is called the Stephen's constant, 5.669 or 5.67 times 10 to the negative 8. So you see all that in this formula. This is the formula for radiation. Quantity of heat radiated divided by time. That's the Stephen's constant. This is emissivity. This is the surface area. This is the temperature of the object in Kelvin. And then the temperature of the surroundings in Kelvin. So there you have the Stephen's constant. All units given. Then you have the emissivity, the area, And you see the temperature both in Kelvin, and it's raised to 4. Do not forget that. It's raised to 4. Minus, again, temperature of the surroundings raised to 4. So when you do those calculations, please do it carefully. Do this part first in a calculator. Write it down on a piece of paper. Do not try to do everything without taking your hands off the calculator keys. That could be disastrous. So, I mean, it's up to you. But write this down. Just find this first and write down, and then multiply with these quantities, and you would get 21.7 kilowatts. The negative there is just to show that it's losing heat. Okay, it's losing heat, so that's why the negative comes in there. Okay, that's specifically mentioned. So that is the problem in radiation. Let's go to number 11. Suppose you walk in a sauna that has an ambient temperature of 50 Celsius. Calculate the rate of heat transfer to you by radiation given your skin temperature is 37 degrees Celsius, the emissivity of skin is 0.98, the surface area of your body is 1.50 meters squared. So now this time the sauna is radiating heat, but your body is absorbing heat by radiation. So it says calculate the rate of heat transfer to you by radiation. Your skin temperature is given. The sauna temperature is T2, and you are the surrounding, so T1 is 37. And it has to be in Kelvin. So you will see all that. Same formula, Q by T, sigma E A, T2 raised to 4 minus T1 raised to 4. That is sigma, Stephan's constant. This is the emissivity that is given as 0.98. Yep, it's given here as 0.98. And then you have the area, 1.50 meters squared. This is the temperature of the sauna in Kelvin, raised to 4, remember, minus temperature of the body in Kelvin raised to 4. It's 137 watts. So you get 137 joules per second. And the B part says, if all other forms of heat transfer are balanced, the net heat transfer is 0. At what rate will your body temperature increase if your mass is 75 kilograms? Oh, now since the heat is coming in, the body temperature is going to increase. Now, this is a case of the body absorbing heat. So once again, we use Q is equal to mc delta T, where m is the mass of the body, and Q we already calculated is 137 watts. See that? When you use that formula, make delta T the subject, and by T from both sides cancels out. So you have 137, mass of the human body, specific heat of the body now, specific heat of the human body. Notice it's close to that of water. Not so close, but it's because 75% of the human body is water. That's why. And then you get that much per second, or the body temperature changes by 0.0314 Celsius per minute. When you stand there longer in the sauna, you're going to get to a much higher temperature, obviously, because every minute your temperature is increasing by that much. Okay, I hope that makes sense. That brings us to number 12. This is about the sun. The sun radiates like a perfect black body with an emissivity of exactly 1. So a perfect black object has an emissivity of 1. Calculate the surface temperature of the sun, given that it's a sphere with 7 times 10 to the 8 meter radius, that radiates a lot of heat, 3.80 times 10 to the 6 watts into 3K space. So let's do it part by part. So that's part A. Calculate the surface temperature of the sun. So the sun is radiating. You have that temperature. It's a formula for radiation. Let's go try to do this. Q by T is sigma EAT raised to 4. You've seen that? You're trying to find the temperature of the surface of the sun. Notice one thing here. The surrounding temperature is taken as 0 Kelvin because it's radiating into what? Into what? Into space. So that's why that temperature is taken as 0. All right. So therefore, you get T is this. This number is given. That's how much it radiates per second. Divide by sigma. And then E. Why is E missing? Because E is 1. Yeah. Emissivity is 1, so that's not written. And then it's a sphere. The sun is a sphere. The surface area of a sphere is 4 pi r squared. 4 pi r squared. So you have 4 pi, the radius squared. That gives you 5.74 times 10 to the 3. Okay? 5.74 times 10 to the 3 Kelvin. That's the surface temperature of the sun. And the B part says, how much power does the sun radiate per square meter of its surface? Well, you just need to divide by the surface area, because if that's how much it radiates, so we know that it radiates this much from all of its area, divided by 4 pi r squared, you would get how much it radiates from 1 meter squared, correct? Yeah, that gives you 6.17 times 10 to the 7 watt per meter squared. And then the third part says, how much power in watts per square meter is that value at the distance of Earth, which is 1.50 times 10 to the 11 meters away. This is the solar constant. So how much does the Earth get? So now what we need to do is imagine. So that's the sun, that's the Earth. Now imagine that there is a sphere which has a radius equal to the distance between the sun and the Earth, surrounding the sun. You see, you have a sphere which has a radius equal to the distance between the sun and the Earth, surrounding the sun. So we can find the surface area of that sphere and then just divide with that number. That's what is done. So that's how much the sun radiates, divided by 4 pi times, notice this, that is the distance between the sun and the Earth. That's squared, and that would give you how much the Earth receives. So look at that. The sun radiates that much per meter squared, but the Earth receives only that much per meter squared, because it's a long, long distance away. But still, that's a lot of energy. So that's 11. So that's taking us to what? Number 12? That was number 12. All right, I got my numbers wrong. So that's number 12. I hope you understood all these questions in this chapter. We dealt with 3 formulas: specific heat, conduction, and radiation. In some of these problems, they came together. But step by step, if you look at it, it's understandable. Thank you, and see you on the next video.